Welcome to Mrs. Z's Chemistry. In this video, we will continue our discussion on cations, talking about more than one type of cation, as well as ionic compound properties, and learning how to name them. So some atoms can only make one cation, which means one type of charge, either a +1 or a +2. Other atoms, though, the elements in the transition metal section of the periodic table, can make more than one cation, which means more than one type of charge, either a +1 or a +2 or +3, sometimes even up to a +7. The only way we can figure out what charge these elements make is by looking at the anion that the cation is making a compound with. So in this example of CuBr2, the bromine always only makes a -1 charge. We have two bromines, therefore the total from bromine is -2. In order to be a neutral compound, the copper must be a +2. Pause to see if you can find the charge on each of the following cations. Here's the answers. In this compound, we only have one bromine with a -1 charge, therefore the copper must be a +1. In this compound, oxygen always only makes a -2, therefore the one iron must equal +2. In this compound, we have 3 oxygens, each making a -2, so the total is -6. The 2 irons then must equal +6, making each iron a +3. Same thing for this one here. Each of the 5 oxygens have a -2 charge, therefore we have a total of -10 from all of the oxygens. The 2 manganese atoms must equal +10. This means that each manganese atom will make a +5 charge. Now let's look at some of the ionic compound properties. Ionic compounds are almost always solids, and that's because they melt at super high temperatures. Sodium chloride, NaCl, is the most common ionic compound we've probably come across in our lives. It's table salt. NaCl melts, becomes a liquid at almost 1500 degrees Fahrenheit, and it boils at almost 2700 degrees Fahrenheit. Hopefully, you will never come across that high of heat. When solid, the ionic compounds do not conduct electricity, but when they are molten, which means liquid, they do conduct electricity. And the reason why is this. Let's look at the solid crystalline structure here on the left. You can see that each of the positive-negative particles are in their interchanging fashion in the lattice structure. But when it's molten, or in the liquid phase, the particles are still super close to each other, but they're moving around each other. They're not stuck in a lattice structure. And that is why when the ions are in a fixed lattice structure and cannot move, then they can't conduct electricity, because electricity is the movement of electrons, or the negative-positive particles. And this is why that the ions can, when they are molten, they can now move freely and conduct electricity. All right, let's learn how to name the ionic compounds. These are fairly simple. We're going to name the cation, then we name the anion, but we change the ending of the anion to ide, I-D-E, and that's it. The cation is the positively charged atom, and it always goes first, both in the chemical compound and in the name. So looking at this first one, CaCl2, we're going to name the cation calcium, and then we name the anion, which is chlorine, and we change the ending to ide. So we would write chloride. Pause to see if you can name each of these ionic compounds. Here are the names. Notice that we do not say dichloride. Calcium dichloride is incorrect. We just say calcium chloride. Same thing over here. We don't say dilithium sulfide. We just say lithium sulfide. The reason is because these ionic compounds must be neutral, and each of these elements only make one type of charge. Lithium is always a +1, and sulfur is always a -2. So the ratio between lithium and sulfur must always be 2 lithiums for every sulfur. Just plain LiS doesn't exist. Therefore, we will never get confused about what lithium sulfide is. We always know that it must come in the ratio of 2 to 1. Same thing is true for each of these other compounds that include a subscript 2. Never use prefixes for ionic compounds. All right, so what about the ionic compounds that include a variable charge cation, one of the transition metals that can change their charge or have a different charge in different compounds? Well, we're going to use a Roman numeral for the charge on the cation. The charges of the cation typically only go up to a +7, so we only need to remember the Roman numerals from 1 to 7. Let's go ahead and review them. 1 is an I, a 2 is 2 I's, 3 is 3 I's, a 5 is a V, a 4 is the V with an I to the left-hand side, which means you subtract 1 from 5. 6 is a V with an I on the right-hand side, and then 7 would be an I with 2 I's on the right-hand side. So this is 1, 2, 3, 4, 5, 6, 7. Typically in chemistry, that's about all you need to know for the Roman numerals. All right, so let's figure out what the charge is on the iron in Fe2O3. Well, from the first slide from this video, we already figured out that the iron has a 3+ charge, but let's talk about it more specifically. Look at the fact that we have 3 oxygen atoms. They each have a -2 charge. The total from oxygen, then, is a -6. The total from the irons must equal +6, and we only have 2 iron atoms. Therefore, the charge on each iron atom must be a 3+ in order to make a neutral compound. So let's go ahead and look at this. We're going to name the iron. We don't change the name of the cation. This iron has a 3+ charge, so we put a Roman numeral 3 in parentheses right next to the iron. Then we write oxide. Notice that the Roman numeral 3 does not mean that we have 3 iron atoms, because we don't. We only have 2 of them. The 3 Roman numeral means each iron atom has a 3+ charge. All right, let's look at the next FeO, or the next iron oxide element, compound. We can't name both of these iron oxide because they are 2 different chemical compounds with different properties, and they're going to react differently with other substances. So we can't call them both iron oxide. That would be confusing. The first one is iron 3 oxide because the iron has a 3+ charge. The next one only has 1 oxygen with a -2 charge. Therefore, the iron must be a +2 charge to make a neutral compound. So we're going to label this iron with a Roman numeral 2 oxide. So this is called iron 2 oxide. Again, the Roman numeral 2 does not mean we have 2 irons, because we don't. We only have 1 iron. The 2 Roman numeral means we have a 2+ charge on the iron atom. Pause to see if you can figure out the names for the remaining ionic compounds listed on this slide. So here's the names. We have manganese 7 oxide. Each manganese atom has a 7+ charge here. We have copper 2 chloride. Not because we have 2 coppers, we don't. We only have 1 copper. But each copper has a 2+ charge. Here's manganese 2 phosphide. Each manganese atom has a 2+ charge. Then here's cobalt 3 fluoride. The cobalt has a 3+ charge. Here's a list of ionic compounds that we probably have in our house. Sodium chloride, of course, we've already looked at that. That's just ordinary table salt. Potassium iodide is the iodine that's added to salt for thyroid health. Sodium fluoride is the ingredient in toothpaste. That's how we get fluoride in our toothpaste. Sodium bicarbonate is baking soda. We probably have that in our kitchen. Sodium carbonate is used in cleaning agents. A lot of these are either food additives, preservatives, anti-caking agents, or ingredients in cleaners. We come across ionic compounds a lot in our lives. All right, let's end with this picture. The top set of test tubes is a sample of each of these metals in their solid neutral form. Scandium, titanium, vanadium, all the way through copper and zinc. They each have kind of a dullish, sometimes a little bit shiny, silver grayish color. Of course, copper is the brassy look there. But when each of these elements are in their ion form, They are dissolved in water. You can't just have a pile of iron with a +2 charge or +3 charge just dry. It must be dissolved in water in order to be an ion. And they make these often very beautiful colors when they are dissolved in water as ions.